What if everything you thought you knew about reality was just the surface of something far stranger? Picture this: a single atom, so small that millions could dance on the head of a pin. Yet within it lies a whirlwind of particles appearing and vanishing in an instant, governed by rules that seem to rewrite the very fabric of existence. This isn't science fiction. This is the quantum world, a hidden dimension of reality where the ordinary laws of physics twist and bend, where particles communicate across vast distances faster than light, and where the act of observing something can change its very nature. It's a realm so counterintuitive that even Einstein called it spooky, yet it's the foundation of everything: the stars above us, the devices in our hands, even the cells in our bodies. Now think about this: the universe with its swirling galaxies and cosmic mysteries might seem vast and untouchable, but its deepest secrets aren't written in the distant heavens. They're buried in the unimaginably small, in the quantum vibrations that hum beneath the surface of reality. Every time you look up at the night sky, you're seeing the echoes of a quantum symphony, a dance of particles that began at the dawn of time. How can something so tiny shape something so enormous? That's the puzzle we're about to unravel. From the strange duality of light acting as both a wave and a particle, to the mind-bending concept of entanglement, where particles mirror each other instantly across the cosmos, the quantum world is a place where logic takes a backseat to wonder. And here's the most astonishing part: we're not just passive observers of this quantum realm. We're part of it. Every thought, every sensation, every heartbeat is a ripple in this microscopic ocean. So today, we're not just exploring abstract theories or equations scribbled on a chalkboard. We're stepping into a story that connects all of us, a journey into the heart of reality itself. By the time we're done, you'll see the universe in a whole new light, one where the boundaries between the tiny and the infinite blur into something extraordinary. Ready to take the plunge? Let's begin. If you think the quantum world sounds like something out of a dream, you're not alone. Even the scientists who first uncovered its mysteries struggled to believe what they were seeing. Take superposition, for example, the mind-bending idea that a particle can exist in multiple states at the same time, like a spinning coin that simultaneously heads and tails until you catch it. Or entanglement, where two particles become mysteriously linked so that changing one instantly affects the other, no matter how far apart they are. These aren't just quirks of nature, they're the fundamental rules of reality at its smallest scale, and they force us to rethink everything we thought we knew about how the universe works. One of the most famous demonstrations of quantum weirdness is the double-slit experiment. Imagine firing tiny particles like electrons at a barrier with two narrow slits. You'd expect them to pass through one slit or the other, creating two distinct bands on a screen behind it. But that's not what happens. Instead, the particles create an interference pattern, like ripples overlapping in a pond, as if they're behaving like waves, not particles. Even stranger, if you try to observe which slit each electron goes through, the interference pattern vanishes. The particles suddenly act like tiny marbles again, as if they know they're being watched. This experiment isn't just a curiosity, it's proof that at the quantum level, particles don't have definite properties until we measure them. This leads us to the Copenhagen Interpretation, one of the earliest attempts to make sense of the quantum world. Proposed by Niels Bohr and Werner Heisenberg, it suggests that particles don't have fixed states until they're observed. Before measurement, they exist in a blur of probabilities, a haze of potential outcomes. It's as if reality itself is undecided, waiting for someone to look before settling into place. This idea was so radical that even Einstein rejected it, insisting that God does not play dice with the universe. But decades of experiments have confirmed again and again the quantum world doesn't care what makes sense to us. And here's the truly astonishing part. these quantum rules aren't confined to some far-off laboratory. They're at work inside your phone, in the lasers that read barcodes, even in the photosynthesis that powers every leaf on Earth. The universe isn't just built on quantum mechanics, it runs on it. So when we say the microscopic world defies common sense, what we're really saying is that our everyday intuition is just a tiny slice of a much bigger, much weirder reality. A quantum enigma isn't a puzzle to solve, it's a doorway, inviting us to see the universe in a whole new way. At the turn of the 20th century, physics stood on the brink of a revolution, one that would shatter centuries of classical thinking. It all began with a problem so mundane it was almost laughable. Scientists couldn't explain why a hot piece of metal glowed red, then white as it heated up. According to the physics of the time, the energy emitted should have been infinite, a result so absurd it became known as the ultraviolet catastrophe. Enter Max Planck, a reluctant revolutionary. In desperation, he proposed a radical solution. What if energy wasn't a smooth, continuous flow, but came in tiny, indivisible packets? He called these packets quanta, and though he saw it as nothing more than a mathematical trick, this idea would crack open the door to an entirely new universe. Planck's quanta were just the beginning. A few years later, a young patent clerk named Albert Einstein took the idea and ran with it. He suggested that light itself wasn't just a wave, as everyone believed, but could also behave as a stream of particles, what we now call photons. This bold claim explained the photoelectric effect, where light hitting metal could knock electrons loose, but only if the light's color, not its brightness, was just right. Wave theory couldn't explain this, but particles could. For this insight, Einstein won the Nobel Prize, though even he hesitated to accept the full implications of his own discovery. The quantum genie was out of the bottle, and there was no putting it back. By the 1920s, the quantum revolution was in full swing, led by a generation of physicists who embraced the strangeness. Werner Heisenberg, barely in his 20s, took the next leap with his uncertainty principle. Imagine trying to measure a hummingbird's position and speed at the exact same moment. The more precisely you pin down its location, the less you know about its momentum, and vice versa. Heisenberg showed this wasn't a limitation of our tools, but a fundamental property of reality itself. At the quantum level, particles don't have definite positions or speeds until we measure them. It's as if the universe thrives on ambiguity, refusing to be pinned down. These breakthroughs didn't just rewrite textbooks, they reshaped technology. Planck's quanta led to the understanding of atomic spectra, the unique fingerprints of elements that let us decipher the composition of stars. Einstein's photons paved the way for lasers, those beams of coherent light that now read barcodes, perform surgeries, and even stream data through fiber optic cables. And Heisenberg's uncertainty principle, it's the reason we can't build perfect transistors forever. There's a quantum limit to how small they can get. What started as a puzzle about glowing metal became the foundation of modern life, proving once again that the deepest truths often hide in the smallest details. The birth of quantum mechanics wasn't just a scientific revolution, it was a reminder that reality, when examined closely, is far more mysterious than we ever imagined. Schrödinger's cat isn't just a quirky thought experiment, it's a doorway into one of quantum mechanics' most perplexing truths. Picture a sealed box containing a feline, a vial of poison, and a radioactive atom. If the atom decays, the poison is released and the cat dies. If not, the cat lives. But here's the twist. Until someone opens the box, quantum rules insist the atom exists in a superposition, both decayed and not decayed, meaning the cat is unthinkably both alive and dead at the same time. This isn't just a paradox, it's a direct challenge to our everyday understanding of reality. We're used to objects having definite states. A light is either on or off, a coin lands heads or tails. But in the quantum realm, certainty dissolves into a cloud of possibilities. What makes this idea so unsettling is that it forces us to confront the role of observation. In the macro world, a tree falling in the forest makes sound whether anyone hears it or not. But in Schrödinger's box, the cat's fate seems tied to whether someone looks inside. This mirrors the behavior of particles, which only choose a definite state when measured. It's as if reality itself hesitates until pressed for an answer. The thought experiment wasn't meant to suggest cats defy biology. It was a critique of the Copenhagen Interpretation, highlighting how absurd quantum rules seem when scaled up to everyday objects. Yet, decades later, labs routinely create superpositions with atoms and photons, proving the phenomenon is very real. The real mystery lies in where we draw the line. Why don't we see tables or planets in superpositions? One compelling answer is decoherence, the idea that interactions with the environment collapse quantum states almost instantly for large objects. A cat is constantly jostled by air molecules, bathed in light and radiating heat, all of which disrupt delicate quantum effects. But isolate an electron in a vacuum and superposition can persist. This suggests the universe has two sets of rules, one for the tiny and isolated, another for the big and messy. Some physicists argue Schrödinger's cat reveals a deeper truth, that quantum mechanics is incomplete. Hidden variables, parallel universes, or even conscious observation might play roles we don't yet grasp. The many worlds interpretation, for instance, proposes that every quantum possibility branches into a new reality. In one universe, the cat lives, in another, it dies. Neither outcome is more real than the other. While this sounds like science fiction, it's a serious attempt to reconcile quantum weirdness with a deterministic cosmos. What's undeniable is how this paradox reshapes our view of existence. The universe isn't a clockwork machine but a tapestry of probabilities, where observation stitches one thread into reality. From quantum computers harnessing superposition to perform calculations at lightning speed, to encryption protocols that rely on the fragility of quantum states, these ideas aren't just philosophical, they're the bedrock of tomorrow's technology. So the next time you flip a light switch, remember, beneath the familiar hum of everyday life, the quantum world hums with infinite possibilities waiting to be seen. Albert Einstein wasn't easily rattled, but quantum entanglement left him deeply unsettled. Imagine two coins flipped simultaneously on opposite sides of the galaxy, somehow always landing matching sides, heads with heads or tails with tails instantly, as if space and time didn't exist between them. That's the essence of entanglement, a phenomenon so bizarre that Einstein dismissed it as spooky action at a distance. Yet, against all intuition, this cosmic choreography isn't just real, it's the backbone of technologies that could revolutionize our future. The magic, or perhaps the mystery of entanglement, lies in its defiance of classical physics. Take two electrons created together, their spins intrinsically linked. Separate them by light years, and measuring one's spin instantly determines the other's, no matter the distance. It's as if the universe maintains an invisible thread between them, weaving connections faster than light could ever travel. This isn't just theoretical. Experiments have confirmed it repeatedly, like the groundbreaking work of Elaine Aspect in the 1980s, where entangled photons mirrored each other's states with eerie precision. But here's the catch: entanglement doesn't actually violate relativity. While the correlation between particles is instantaneous, no usable information is transmitted. You can't send a message faster than light using entangled pairs because the outcome of each measurement remains random until compared. It's like having two envelopes, one containing a black marble and the other white. Opening one reveals the other's contents, but you didn't control what went inside. This subtle distinction preserves Einstein's cosmic speed limit while leaving us with a profound puzzle. How does nature orchestrate this synchronized dance? One compelling clue comes from the mathematics of quantum mechanics. Entangled particles aren't just correlated, they're described by a single, shared quantum state. It's not that one particle talks to the other, they exist as a unified system even when separated. Think of it like a pair of gloves. If you find one left-handed glove in your pocket, you instantly know the other is right-handed, not because of some signal between them, but because their identities were linked from the start. The universe, it seems, operates on a level where individuality blurs into interconnectedness. Today, entanglement isn't just a laboratory curiosity, it's the engine behind quantum technologies. Quantum computers leverage entangled qubits to perform calculations at speeds unimaginable to classical machines, solving problems like drug discovery or climate modeling in days instead of centuries. Quantum cryptography uses entanglement to create unbreakable codes, where any eavesdropping attempt disrupts the delicate quantum link, alerting the sender. Even more tantalizing are theories suggesting entanglement might be woven into spacetime itself, with some physicists proposing it as the glue holding the universe's geometry together. So what does this mean for our understanding of reality? Entanglement hints that the universe is far more interconnected than it appears, with separations between objects perhaps being illusions. It challenges us to rethink not just how particles interact, but the very nature of space and time. Could entanglement be a glimpse into a deeper layer of existence where all things are fundamentally linked? For now, the answers remain as elusive as the phenomenon itself, but one thing's certain: the quantum world never stops surprising us. What if every choice you've ever made, every path taken or not taken, exists simultaneously in an infinite web of realities? This isn't the plot of a sci-fi movie. It's the bold claim of the many worlds interpretation, a provocative solution to quantum mechanics' strangest puzzles. Picture Schrödinger's cat again, but with a twist. Instead of the cat being both alive and dead until observed, the universe splits into two branches, one where the cat survives, another where it doesn't. No collapse of probabilities, no reliance on observers, just an ever-expanding tree of alternate timelines, each equally real. Hugh Everett, the Princeton physicist who proposed this idea in the 1950s, didn't set out to rewrite reality. He was simply trying to sidestep the messy role of observation in quantum theory. In the Copenhagen Interpretation, particles snap into definite states only when measured, leaving us to wonder what counts as a measurement. A human eye, a machine? Everett's answer was elegant and unsettling. He argued that every possible quantum outcome does happen, but in a newly spawned universe. That radioactive atom in Schrödinger's box, it decays in one world and doesn't in another, with both versions of reality unfolding independently. Critics dismissed Everett's work as metaphysics, not physics. Even Niels Bohr, the godfather of quantum theory, reportedly brushed it aside. But over time, the idea gained traction, especially among those wrestling with the measurement problem. If quantum mechanics governs everything, why should tiny particles obey probabilistic rules while larger objects like cats or lab equipment don't? Many worlds eliminates this divide by treating all outcomes as equally valid, just separated by the branching of reality itself. Think of it like a choose-your-own-adventure book where every possible decision is followed, spawning endless parallel narratives. Toss a quantum coin, and in one universe it lands heads, in another tails. But here's the kicker: these branches aren't science fiction. They're encoded in the math of quantum mechanics, woven into the equations physicists use every day. The catch: we can't access them. Once a branch splits off, it's forever beyond our reach, like a radio signal tuned to a frequency we can't hear. Some physicists argue this makes many worlds untestable, a theory in name only. But others see tantalizing hints. Quantum computing, for instance, relies on manipulating superpositions to perform calculations. Could those calculations be happening across multiple worlds, with the computer harnessing the power of parallel realities? Or consider cosmic inflation, the theory that our universe ballooned from a tiny speck after the Big Bang. If inflation can happen once, why not infinitely, creating a multiverse where every quantum possibility plays out? The philosophical implications are staggering. If countless versions of you exist, some slightly different, others unrecognizable, what does that mean for free will? For identity, the many worlds interpretation doesn't just challenge our understanding of physics, it forces us to confront the nature of existence itself. Maybe the universe isn't a single, linear story, but an endless library of every story that could ever be told. And if that's true, the quantum world isn't just beneath reality, it is reality unfolding in ways we're only beginning to glimpse. Quantum field theory is like discovering that the universe is woven from invisible threads that hum with potential, shaping everything from the light in your screen to the gravity holding planets in orbit. Picture space not as an empty stage, but as a vibrant, seething ocean of fields, each one a kind of cosmic fabric stretching endlessly in all directions. What we call particles, electrons, photons, even the elusive Higgs boson, are just ripples in these fields, like waves rising and falling on the surface of a deeper, hidden sea. This elegant idea doesn't just explain the building blocks of matter, it reveals how they dance together, governed by rules that blend quantum weirdness with Einstein's relativity. Take the electromagnetic field, for instance. It's everywhere, even in what we think of as empty space. When this field vibrates just right, it creates photons, particles of light that let you see these words. But here's where it gets stranger. These fields aren't passive backdrops, they're dynamic, interacting forces. An electron, for example, is a tiny knot of energy in the electron field, and its electric charge comes from how it tangles with the electromagnetic field around it. It's as if every particle is a note in a grand symphony played by the fields themselves. Then there's the Higgs field, perhaps the most famous of them all. Unlike other fields, it doesn't just create particles, it gives them mass. Imagine wading through a pool of molasses. The resistance you feel is akin to how particles like quarks or electrons drag against the Higgs field, acquiring mass in the process. Without this field, atoms wouldn't hold together, and the universe as we know it would vanish into a blur of weightless, racing particles. The discovery of the Higgs boson in 2012 wasn't just a triumph of engineering, it was proof that these invisible fields are more than mathematical abstractions. They're the scaffolding of reality, yet for all its power, quantum field theory leaves us with haunting gaps. Why are there so many fields, each with its own quirks and strengths? And what about the quantum vacuum, the lowest energy state of these fields, where particles flicker in and out of existence like cosmic fireflies? This isn't true emptiness, it's a seething foam of potential where pairs of particles and antiparticles spontaneously emerge, only to annihilate moments later. Some theories suggest dark energy, the mysterious force accelerating the universe's expansion, might be a property of this vacuum itself, as if space itself is pushing outward from within. The deeper we probe, the more quantum field theory blurs the line between something and nothing. It suggests that what we perceive as solid and stable is really a shimmering illusion, a temporary arrangement of energy in an endless, fluctuating tapestry. And if that's true, then the real mystery isn't just how particles behave. It's why the universe chose these particular fields, these specific rules, to weave the story we call existence. One thing's certain, the answers, when they come, will rewrite not just physics, but our very sense of what it means to be real. Think of the emptiest place you can imagine, a void so vast it stretches beyond sight. Now here's the twist, that emptiness is an illusion. According to quantum mechanics, even the deepest vacuum of space is anything but empty. It's a bubbling cauldron of activity where particles and antiparticles flicker into existence for fleeting moments before vanishing again. This phenomenon, known as quantum foam, isn't just theoretical. It leaves fingerprints on the universe, shaping everything from the behavior of atoms to the fate of the cosmos itself. Heisenberg's uncertainty principle tells us that on the smallest scales, energy can't be pinned down precisely. There's always a tiny, inherent fuzziness, a wiggle room in the fabric of reality. This allows pairs of virtual particles to spontaneously emerge from the void, borrowing energy from nothingness before annihilating each other and repaying the debt. It's like a cosmic game of now you see it, now you don't, happening trillions of times per second in every cubic inch of space. These aren't just mathematical quirks, they have real-world consequences. Take the Casimir effect. Place two metal plates extremely close together in a vacuum, and they'll be pushed toward each other by the sheer pressure of virtual particles outside the gap where more fluctuations can occur. It's as if the vacuum itself is flexing its muscles, proving it's far from inert. Then there's the Lamb's shift, a tiny but measurable tweak in the energy levels of hydrogen atoms. Without virtual particles flitting around, electrons would orbit nuclei in predictable, textbook-perfect paths. But the quantum vacuum's chaos nudges them slightly off course, a deviation confirmed by experiments in the 1940s. These aren't minor details, they're proof that what we call nothing is actually a dynamic, participatory part of the universe. Perhaps most astonishing is the link between quantum foam and dark energy, the mysterious force accelerating the expansion of the cosmos. If you add up all the energy tied to these vacuum fluctuations, you'd expect it to exert a gravitational effect, either pulling the universe together or pushing it apart. Some theories suggest dark energy might be the residual hum of this quantum activity, a kind of background pressure embedded in space itself. But here's the puzzle. Calculations predict a vacuum energy trillions of times stronger than what we observe. This mismatch, called the cosmological constant problem, is one of physics' greatest unsolved mysteries. Is our math wrong? Are we missing a hidden mechanism that cancels out most of this energy? Or is there a deeper layer to the vacuum we haven't uncovered yet? The quantum vacuum challenges our most basic assumptions about reality. It hints that the universe isn't built on a static stage, but on a living, breathing medium where nothing is always doing something. From the forces between atoms to the expansion of galaxies, its influence is everywhere. And if we can decode its secrets, we might finally understand why the cosmos looks and behaves the way it does. The vacuum isn't empty, it's the hidden engine of existence, whispering clues about the nature of everything. Black holes aren't just cosmic vacuum cleaners, they're the ultimate testing ground for the laws of physics, where quantum mechanics and gravity collide in ways that defy logic. Take Hawking radiation, one of the most startling discoveries in modern science. Stephen Hawking realized that black holes aren't completely black. Thanks to quantum fluctuations near the event horizon, they slowly leak particles, losing mass over time until they evaporate entirely. But here's the catch: if a black hole vanishes, what happens to all the information it swallowed? According to quantum mechanics, information can't be destroyed. It can change form, but it must persist. Yet Hawking's calculations suggested it simply disappears. This contradiction, known as the information paradox, has haunted physicists for decades, threatening to unravel our understanding of reality itself. At the heart of the paradox is a clash between two pillars of physics. Quantum mechanics insists that information is sacred, preserved in the universe like an unbreakable code. But general relativity, Einstein's theory of gravity, treats black holes as one-way streets. Once something crosses the event horizon, it's gone for good, its details lost in the singularity. Hawking radiation seemed to confirm this grim fate, implying that the history of a fallen star or a doomed spacecraft is erased from existence. The implications are staggering. If black holes really destroy information, then the universe is fundamentally unpredictable, and quantum theory, the framework behind everything from chemistry to computers, is incomplete. Desperate for answers, physicists have proposed wild solutions. One idea is the holographic principle, which suggests that all the information swallowed by a black hole isn't lost but encoded on its surface like a cosmic fingerprint. Imagine a three-dimensional object projected onto a two-dimensional screen. The details are compressed but still intact. In this view, the event horizon acts as a hologram, storing data about everything inside it. Then there's the firewall hypothesis, which posits a searing wall of energy at the black hole's edge, incinerating anything that crosses. It's a radical fix, but it comes with its own problems, like violating Einstein's prediction that falling into a black hole should feel uneventful, at least until gravity does its gruesome work. The stakes couldn't be higher. Solving the information paradox might finally bridge quantum mechanics and gravity, revealing a unified theory of everything. Some researchers think the answer lies in quantum entanglement, with particles inside and outside the black hole remaining mysteriously linked, preserving information in their invisible threads. Others argue that black holes don't fully evaporate but leave behind tiny remnants, capsules holding all the secrets they ever consumed. What's clear is that black holes aren't just celestial oddities, they're cosmic puzzles, pressing us to rethink the nature of space, time, and information itself. Every photon they emit, every paradox they present, is a clue waiting to be decoded. And when we finally crack their secrets, we won't just understand black holes, we'll understand the universe on a level we can barely imagine today. String theory turns the quantum world into a cosmic symphony, one where the universe's tiniest building blocks aren't dots but strands of energy, vibrating at different frequencies like the strings of a violin. Pluck one string and you get an electron, pluck another and you have a quark. It's a breathtakingly elegant idea, suggesting that the dizzying variety of particles we observe might just be different notes in a grand, unified composition. But here's where the melody takes a surprising turn. For the math to work, these strings can't just wiggle in the 3 dimensions we know. They need extra ones curled up so small we've never noticed them. Imagine an ant crawling along a telephone wire. From far away, the wire looks one-dimensional, but up close, it's a thick cylinder with hidden circumference. Could our universe be like that, with 6 or 7 extra dimensions folded into the fabric of space-time? The allure of string theory isn't just its elegance, it's its ambition. For decades, physicists have struggled to reconcile the two titans of modern physics: quantum mechanics, ruling the subatomic world with probabilities and particles, and general relativity, governing stars and galaxies with the curvature of spacetime. Gravity refuses to play nice with quantum rules, and no amount of tweaking has fixed the mismatch, but strings might. In this framework, gravity emerges naturally from the vibrations of closed loops, weaving seamlessly into the quantum tapestry. It's as if the theory whispers, the conflict was never real, you were just missing the bigger picture. Yet for all its promise, string theory has a thorny problem. How do you test an idea that lives in dimensions we can't see? The scales involved are unimaginably tiny. Strings are thought to be about 100 billion times smaller than an atom. Even our most powerful particle colliders can't probe that realm directly. Some researchers hope for indirect evidence, like finding signatures of extra dimensions in high-energy cosmic rays or spotting microscopic black holes in experiments. Others turn to math, exploring the theory's intricate geometries for clues about why our universe has the properties it does. One fascinating prediction is the landscape of possible solutions, a vast array of potential universes, each with different physical constants. If true, it would mean our cosmos is just one page in an infinite cosmic library. Critics argue this makes string theory untestable, more philosophy than science. But its defenders counter that great ideas often outpace technology. Think of Einstein's prediction of gravitational waves, confirmed a century later. What's undeniable is how string theory has reshaped physics, spinning off breakthroughs in black hole thermodynamics, quantum field theory, and even pure mathematics. Those hidden dimensions might be more than mathematical fiction. They could be the scaffolding of reality itself, waiting for us to find the right lens to see them. Whether string theory ultimately unifies physics or gives way to something stranger, it's taught us one vital lesson: the universe's secrets are rarely where we expect them to be. If string theory is a symphony of vibrating strings, then loop quantum gravity is more like a cosmic tapestry, a universe stitched together from tiny, indivisible threads of spacetime itself. While string theory adds hidden dimensions to the quantum puzzle, loop quantum gravity takes the opposite approach. It suggests that space isn't smooth and continuous but made of finite, interwoven loops like the pixels on a screen or the threads in a mesh. At the tiniest scales, these loops form a dynamic network, constantly evolving and connecting, giving rise to the fabric of reality we experience. It's a radical idea, one that doesn't just tweak our understanding of particles but reimagines the very stage they perform on. The roots of loop quantum gravity trace back to a simple yet profound question. What if spacetime itself is quantized? Just as light comes in discrete packets called photons, perhaps space has its own fundamental atoms, tiny units that can't be divided further. The theory builds on Einstein's general relativity, treating gravity not as a force but as the curvature of spacetime, except now that curvature isn't smooth. Instead, it's knitted together from microscopic loops, each carrying a quantum of area or volume. Picture a digital photograph, zoom in far enough, and the image dissolves into individual pixels. Loop quantum gravity proposes that spacetime does the same, with each pixel representing a discrete quantum of geometry. One of the theory's most startling predictions involves black holes. In classical physics, a black hole's singularity, a point of infinite density, is where the laws of physics break down. But loop quantum gravity suggests something different. At the heart of a black hole, spacetime's granularity might prevent true singularities, replacing them with a bounce. Instead of collapsing endlessly, matter could rebound, potentially giving birth to a new universe. It's as if black holes aren't cosmic dead ends but tunnels to somewhere else, an idea that echoes through modern cosmology. Similarly, the Big Bang might not have been a singular explosion but a big bounce, the latest chapter in an endless cycle of universes expanding and contracting. What makes loop quantum gravity particularly compelling is its testability. Unlike string theory's hidden dimensions, the granularity of spacetime could leave fingerprints in the light from distant cosmic events. Gamma-ray bursts, for example, travel billions of years to reach us. If spacetime is pixelated, the highest energy photons might interact with that granular structure in subtle ways, arriving at Earth slightly out of sync with lower energy light. Experiments like the Fermi Gamma-Ray Space Telescope are already hunting for these tiny delays, though the results so far remain inconclusive. Another clue could come from the cosmic microwave background, the afterglow of the Big Bang. If spacetime's quantum structure left imprints there, future telescopes might detect them. Yet the theory faces its own challenges. Merging quantum mechanics with gravity is no easy feat, and loop quantum gravity struggles to explain other fundamental forces like electromagnetism in the same unified framework. Critics argue it's a theory of gravity alone, leaving the rest of physics untouched. But its proponents counter that by starting with spacetime itself, they're tackling the deepest layer of reality first, one stitch at a time. Whether loop quantum gravity or string theory ultimately prevails, or whether some yet unknown idea unites them, the quest to quantize spacetime is more than academic. It's a search for the universe's operating system, the code underlying everything from the spin of electrons to the whirl of galaxies. And if space-time truly is woven from loops, then reality isn't just stranger than we imagine. It's stranger than we can imagine, a fabric forever being rewoven by the quantum loom of existence. Ever reach into your pocket and pull out a coin that's somehow both heads and tails at the same time? Of course, not coins don't behave like quantum particles. But here's the puzzle. If atoms and electrons can exist in multiple states simultaneously, why doesn't that strangeness scale up to the world we see? Why don't baseballs split into two trajectories mid-pitch, or coffee cups hover between the table and the floor? The answer isn't that quantum physics stops working for big objects, it's that the universe has a built-in eraser, constantly wiping away quantum weirdness before we ever notice it. That eraser is called decoherence, and it's the reason reality feels so solid. Picture a drop of ink falling into a glass of water. At first, it holds its shape, a dense, coherent blob. But give it time, and the ink spreads, dissolving into the water until it's everywhere at once, indistinguishable from its surroundings. Quantum coherence works the same way. An isolated electron can maintain its superposition, its delicate balance of possibilities, because nothing disturbs its quantum state. But place that electron in the real world, where it's bombarded by air molecules, light particles, and even cosmic rays, and its quantum ink spreads irreversibly into the environment. The superposition doesn't vanish, it leaks out, becoming so entangled with everything around it that the original state can't be retrieved. What's left is what we perceive, a single, definite outcome. This isn't just theory, it's measurable. In labs, scientists can watch decoherence happen in real time. Cool a tiny object like a nanoscale drum or a cloud of atoms to near absolute zero, shielding it from environmental noise, and it'll briefly behave quantum mechanically, vibrating at multiple frequencies simultaneously. But warm it up slightly, let a few photons bump into it, and the superposition crumbles. The threshold isn't about size, but isolation. A virus, theoretically, could show quantum effects if kept perfectly still and cold. But a dust mote, too jostled by the world, a cat, forget it. The implications stretch far beyond philosophy. Quantum computers rely on maintaining coherence, keeping their qubits in superposition long enough to perform calculations. Yet decoherence is their greatest enemy. Even the slightest thermal vibration or stray magnetic field can disrupt a qubit's fragile state, introducing errors. That's why quantum computers are housed in elaborate freezers, shielded from even the whisper of external influence. It's a race against the universe's tendency to collapse quantum possibilities into classical certainties. But here's where things get thorny. Decoherence doesn't actually explain how a single outcome emerges from the quantum soup. It tells us why we don't see superpositions, but not why we perceive one version of events over another. Some interpretations, like the many worlds theory, argue that every possible outcome does happen just in branching universes we can't access. Others suggest there's a deeper mechanism, a yet unknown law that tips the scales. For now, decoherence remains the best bridge between the quantum and classical worlds, a reminder that reality, at its core, is far more fluid than it appears. The solidity of everyday life isn't a fundamental truth. It's a side effect of living in a noisy, interactive universe where quantum secrets are constantly being spilled. Imagine a computer that doesn't just calculate faster, but explores every possible solution at once, like a library where you can read every book simultaneously instead of one at a time. That's the promise of quantum computing, where the bizarre rules of the quantum world become tools for unimaginable processing power. At its core are qubits, the quantum cousins of classical bits. While ordinary bits are like light switches stuck in either an on or off position, qubits are more like dimmer dials capable of hovering in a blend of states until measured. This isn't just a small upgrade, it's a paradigm shift, enabling calculations that would take today's supercomputers millennia to complete. Take cryptography, for example. Modern encryption relies on the fact that factoring large numbers is brutally hard for classical computers. A 200-digit number might take centuries to crack, but a quantum machine leveraging superposition and entanglement could theoretically solve it in days. That's why governments and corporations are pouring billions into quantum research, racing to build defenses against what might be the ultimate code-breaking tool. Yet it's not all doom and gloom. Quantum computing could also create unbreakable encryption, using entangled particles to detect eavesdroppers instantly. It's a double-edged sword, balancing vulnerability and security in ways we're only beginning to grasp. Then there's material science and drug discovery. Designing new medicines or superconductors often involves simulating molecular interactions, a task so complex that classical computers approximate rather than replicate. Quantum machines, though, could model these systems atom by atom, unlocking treatments for diseases or materials that harvest energy with near-perfect efficiency. Imagine tailoring cancer drugs to individual genetic profiles or crafting alloys that revolutionize energy storage. The potential isn't just incremental, it's transformative. But here's the catch: qubits are fragile. A passing photon or a stray magnetic field can disrupt their delicate states, introducing errors. That's why today's quantum computers are housed in high-tech freezers, shielded from even the faintest interference. Error correction is the field's holy grail, requiring thousands of physical qubits to stabilize a single logical one. Companies like IBM and Google are experimenting with everything from superconducting loops to trapped ions, each approach balancing coherence, time, scalability, and control. Google's quantum supremacy experiment in 2019, where their Sycamore processor solved a problem in minutes that would take a supercomputer 10,000 years, was a milestone, but it also highlighted how far we have to go. The task was esoteric with no practical use, a reminder that useful quantum computing requires not just speed but reliability. The road ahead is both thrilling and uncertain. Will quantum machines ever be stable enough for widespread use? Or will they remain niche tools like particle accelerators, powerful but impractical for daily life? The next decade will test these limits as researchers tackle noise reduction, better algorithms, and hybrid systems that blend classical and quantum computing. One thing's certain: the quantum revolution isn't a single breakthrough but a marathon, with each step revealing new challenges and new possibilities. Whether it reshapes technology or remains a specialized marvel, quantum computing is forcing us to rethink what's computationally possible, pushing the boundaries of both physics and human ingenuity. Think of sending a secret message so secure that the very act of someone trying to intercept it would instantly expose their presence. This isn't spy fiction, it's the reality of quantum cryptography, where the quirks of quantum mechanics become the ultimate guardians of privacy. At its heart lies quantum key distribution, a method that doesn't just resist hacking but detects it with unshakable certainty. Here's how it works. Instead of relying on complex math to scramble data, it uses individual photons of light, each polarized in a specific way to represent bits of a cryptographic key. Thanks to the no-cloning theorem, a fundamental quantum rule, these photons can't be copied without altering their state. Any eavesdropper trying to sneak a peek would inevitably disturb the photons, leaving behind a telltale trail of errors that alerts both sender and receiver. It's like sealing a letter with ink that smudges if touched, revealing tampering before the message is even read. The implications are staggering. Governments and financial institutions are already testing quantum-secured networks, with China launching the 2,000-kilometer-long Beijing-Shanghai quantum communication backbone in 2017. Banks like J.P. Morgan chase experiment with quantum encryption to shield transactions, while satellite-based systems like MISHUS demonstrate unhackable links between continents. This isn't just incremental progress, it's a leap toward a future where sensitive data, from medical records to military secrets, could be shielded by the laws of physics themselves. But there's a twist. The same quantum principles that fortify cryptography might also undermine it. Quantum computers, with their ability to perform parallel calculations on a cosmic scale, threaten to crack the encryption protocols that protect today's internet. Algorithms like RSA and ECC, which rely on the difficulty of factoring huge numbers or solving elliptic curves, could crumble under a quantum attack. Shor's algorithm, a quantum method devised in 1994, would make short work of these systems if large-scale quantum computers ever become practical. The race is already on to develop post-quantum cryptography classical algorithms resistant to quantum hacking before that day arrives. What makes this duel so fascinating is its asymmetry. Quantum key distribution offers perfect security in theory, but its practical implementation faces hurdles like distance limits and photon loss over fiber optic cables. Quantum computing, meanwhile, remains in its infancy, with error-prone machines far from cracking real-world codes. Yet both fields are advancing at breakneck speed, locked in a technological arms race where the stakes couldn't be higher. The ultimate irony, quantum mechanics, once a realm of abstract paradoxes, now holds the keys to both our digital salvation and vulnerability. As researchers refine quantum repeaters to extend secure networks and devise new encryption standards, we're witnessing a profound shift, one where the rules of the subatomic world redefine the boundaries of trust and secrecy. The future of security may not belong to the strongest code, but to the quirkiest particles. What if the universe needs us to look at it before it decides what's real? This isn't science fiction, it's the heart of the measurement problem, a puzzle so profound it blurs the line between physics and philosophy. Picture an electron spinning in superposition, a blur of possible states. The moment you measure it, that blur snaps into a single, definite outcome. But here's the mystery: what counts as a measurement? Is it the click of a detector, the presence of a human observer, or something even stranger? Some interpretations, like von Neumann-Wigner, take a radical stance. Consciousness itself might be the trigger that collapses quantum possibilities into reality. In this view, the universe exists in a haze of potential until a mind, human or otherwise, interacts with it, like a dreamer waking up and solidifying the dream. Nobel laureate Eugene Wigner even proposed a thought experiment where a friend in a lab measures a quantum system. To Wigner, outside the lab, the entire experiment remains in superposition until he learns the result. It's as if reality layers itself dependent on who's looking, but not everyone buys into consciousness as the cosmic referee. Objective collapse theories like Garrodi-Rimini-Weber propose that superpositions break down spontaneously due to random, inherent fluctuations in nature, no observer required. Imagine a sandcastle on the beach. It doesn't need someone to watch it crumble. The wind and waves will do the job eventually. Similarly, quantum states might have a natural expiration date, collapsing under their own weight after a tiny but finite time. Experiments are already hunting for signs of these collapses, like the faint flashes of light they might produce. Then there's the many worlds interpretation, which sidesteps the measurement problem entirely. Instead of collapsing, every possible outcome branches into a new universe. In this scenario, there's no special role for consciousness, just an endlessly splitting cosmos where every quantum dice roll lands all possible ways. It's a dizzying idea, but one that's mathematically elegant, preserving the purity of quantum mechanics without adding extra rules. The debate isn't just academic. If consciousness does play a role in shaping reality, It would mean our minds aren't passive observers but active participants in the universe's unfolding. Ancient philosophies argued that perception creates the world. Quantum mechanics might be pointing us back toward that idea with equations instead of mysticism. On the other hand, if objective collapse or many worlds wins out, reality exists independently of us, vast and untamed. For now, the measurement problem remains open, a reminder that the quantum world refuses to fit neatly into our categories. Whether the answer lies in the human mind, the fabric of space-time, or the infinite branches of parallel universes, one thing's certain: the act of looking doesn't just reveal reality, it might just define it. John Bell's theorem didn't just challenge our understanding of the quantum world, it shattered the very foundations of how we perceive reality. Imagine two dancers separated by an ocean, yet mirroring each other's movements perfectly, instant by instant. Classical physics would say this coordination requires some hidden signal passing between them, some unseen force orchestrating their steps. But Bell's math revealed something far stranger. If quantum mechanics is correct, no such hidden signals, no local hidden variables, could ever explain the eerie synchronicity of entangled particles. His theorem wasn't just an abstract idea, it was a gauntlet thrown down to nature, demanding an answer. Is reality truly as weird as quantum theory suggests? The answer came in a series of landmark experiments, starting with Elaine Aspect's work in the 1980s. By measuring entangled photons at angles chosen randomly and faster than any hypothetical signal could travel between them, these tests closed the loopholes that might have preserved a classical, deterministic universe. The result: the photons defied Bell's inequalities, behaving in ways no local hidden variable theory could explain. It wasn't just a victory for quantum mechanics, it was a funeral for local realism. The comforting notion that objects have definite properties independent of observation and that influences can't propagate faster than light. The universe, it seems, doesn't play by those rules. So what does this leave us with? If particles don't have pre-existing states before measurement, and if their connection isn't mediated by any detectable force, then reality must be either non-local or fundamentally probabilistic, or both. Non-locality means that particles can influence each other across vast distances without any physical mechanism, as if space itself is an illusion. Probabilistic reality suggests that the universe is built on uncertainty, with outcomes not just unknown but undecided until the moment of observation. Einstein's spooky action at a distance wasn't a flaw in quantum theory. It was a feature woven into the fabric of existence. The philosophical fallout is staggering. If Bell's theorem holds, then the universe isn't a collection of isolated objects following predetermined paths. It's a web of interconnected possibilities, where the act of measurement doesn't just reveal reality, it participates in creating it. Some interpretations, like Bohmian mechanics, embrace non-locality, proposing a hidden quantum potential that guides particles in ways we can't directly observe. Others, like the many worlds interpretation, sidestep non-locality by suggesting every possible outcome happens in branching universes, making the need for instant communication irrelevant. Yet the most profound implication might be this: Bell's theorem forces us to confront the limits of human intuition. Our brains evolved to navigate a world of medium-sized objects moving at modest speeds, where cause and effect are clear and separations are absolute. Quantum realm operates on entirely different principles, revealing a cosmos where independence and locality are illusions. This isn't just about physics, it's about redefining what we mean by real. Whether we accept a universe buzzing with instant connections or one that refuses to settle on facts until compelled, one thing is certain: the quantum world isn't just stranger than we imagine. It's stranger than we can imagine, and Bell's theorem is the proof. What if simply watching something could freeze it in time, In the quantum world, this isn't just a thought experiment. It's a real phenomenon called the quantum Zeno Effect, where the act of observation doesn't just reveal reality but actively alters it. Picture an unstable atom on the verge of decaying, like a ticking time bomb. According to quantum rules, its decay isn't instant, it's a gradual process, a probability cloud where the atom exists in a superposition of intact and decayed states. But here's the twist. If you repeatedly measure the atom, checking whether it's still intact, you can effectively trap it in its original state, delaying or even preventing its decay. It's as if time itself pauses under the spotlight of observation. The effect gets its name from Zeno of Elea, an ancient Greek philosopher who argued that motion is an illusion. If you continually divide a journey into smaller moments, an arrow in flight never actually reaches its target. In the quantum realm, this paradox comes to life. Each measurement resets the atom's quantum clock, forcing it back to its starting point before it can fully transition. The more frequently you observe it, the slower it decays, as if reality hesitates under scrutiny. This isn't just theoretical. Experiments with trapped ions and oscillating atoms have confirmed it. In one study, researchers used laser pulses to watch beryllium atoms, stretching their decay time from milliseconds to seconds, a dramatic slowdown driven purely by observation. But what's really happening here? At its core, the Zeno effect exposes the profound link between measurement and quantum evolution. In the absence of observation, a quantum system evolves smoothly, its probabilities shifting like sand in an hourglass. But measurement interrupts this flow, collapsing the system into a definite state and restarting the clock. It's a reminder that in the quantum world, the observer isn't separate from the experiment, they're part of it, shaping outcomes just by looking. Some interpretations even suggest that consciousness plays a role, though this remains hotly debated. Could the Zeno effect imply that reality, at some level, requires attention to persist? The implications stretch far beyond philosophy. Researchers are already exploring how to harness this effect to stabilize quantum computers, where qubits are notorious for losing coherence. By strategically kicking qubits with targeted measurements, scientists might extend their useful lifespan, reducing errors and boosting performance. There's even speculation about using Zeno-like techniques to protect delicate quantum states in communication networks, creating ultra-secure channels resistant to interference. Yet the most tantalizing questions are the deepest ones. Does the Zeno effect hint that time itself is more fluid than we think? Could there be scenarios where observation doesn't just slow decay but stops it entirely, creating a kind of quantum immortality? And if so, what does that say about the nature of reality? Is it a tapestry woven from countless observations, a cosmic dance where nothing truly happens until someone's looking? The Zeno effect doesn't just challenge our understanding of quantum mechanics. It invites us to rethink the very fabric of existence, where watching isn't passive but profoundly creative. The universe, it seems, doesn't just unfold, it responds. Life doesn't just unfold in the warm, messy world of chemistry. It might also dance to the subtle, invisible rhythms of the quantum realm. Consider the humble leaf basking in sunlight. Photosynthesis, the process that powers nearly all life on Earth, is staggeringly efficient, almost too efficient. Classical biology struggles to explain how plants convert sunlight into energy with near-perfect precision, but quantum physics might hold the key. Experiments suggest that photons of light, once absorbed by chlorophyll, don't just bounce around randomly. Instead, they exploit quantum coherence, exploring multiple energy pathways simultaneously to find the most efficient route to the reaction center. It's as if the leaf performs a lightning-fast quantum computation with every ray of sunlight it captures, turning biology into a masterclass in quantum optimization. Then there's the mystery of enzyme reactions, the molecular machines that drive everything from digestion to DNA repair. These reactions happen far faster than classical chemistry predicts, sometimes millions of times faster. The secret, quantum tunneling, where enzymes allow particles like electrons or even entire protons to vanish from one position and reappear in another, bypassing energy barriers entirely. Imagine walking through a wall instead of climbing over it. This isn't just theoretical. Studies of enzymes like alcohol dehydrogenase, which helps break down toxins in our bodies, show tunneling in action. Without it, life as we know it might grind to a halt, its chemistry too sluggish to sustain complexity. But the quantum intrigue doesn't stop there. Take bird migration, where creatures like the European robin navigate across continents using Earth's faint magnetic field. The leading hypothesis involves something called the radical pair mechanism, a quantum effect where light-sensitive molecules in the bird's eye form entangled electron pairs, their spins influenced by the planet's magnetism. This creates a biological compass sensitive enough to detect changes as subtle as a few nanoteslas. If confirmed, it would mean these birds aren't just following instincts, they're tapping into a quantum sense, a sixth faculty beyond our human perception. The most provocative idea, though, lies in the human brain. Some researchers, like physicist Roger Penrose and anesthesiologist Stuart Hameroff, propose that consciousness itself might arise from quantum processes within the brain's microtubules, tiny protein structures inside neurons. Their theory, called orchestrated objective reduction, suggests that these microtubules harness quantum vibrations, collapsing into definite states to generate moments of awareness. It's a controversial claim, with many neuroscientists favoring classical explanations, but it raises a tantalizing question. Could our very experience of self, of thought and feeling, be rooted in quantum phenomena? If these examples hold up, the implications are staggering. Medicine could leap forward with quantum-designed drugs that target diseases at unprecedented precision, or therapies that harness coherence to repair cellular damage. Agriculture might engineer crops that photosynthesize even more efficiently, feeding a growing planet. And our understanding of life's origins could shift. If quantum effects aren't just incidental but essential, then the line between biology and physics blurs in ways we're only beginning to grasp. Yet challenges remain. Quantum effects are fragile, thriving best in cold, isolated environments, not the warm, noisy interiors of living cells. Skeptics argue that decoherence would shred delicate quantum states in biological systems, leaving no room for sustained coherence. But nature, it seems, has found tricks to protect these processes, perhaps through rapid cycles of decoherence and recoherence, or molecular structures that shield quantum states like microscopic Faraday cages. The field of quantum biology is still young, a frontier where every discovery peels back another layer of mystery. Whether it's the precise flicker of an enzyme's tunneling electron or the cosmic navigation of a migrating bird, life might be far more quantum than we ever dreamed. And if that's true, then the boundary between the living and the physical world isn't just porous, it might not exist at all. Dark matter is the universe's most elusive ghost, a cosmic specter that neither emits nor reflects light, yet holds galaxies together with its invisible grip. We've known for decades that stars orbit their galactic centers too fast to be explained by visible matter alone. The math is clear. There must be 5 times more dark matter out there than the ordinary atoms making up planets, stars, and us. But what is it? The leading theories point to the quantum realm, where exotic particles born from undiscovered fields might be hiding in plain sight. Take actions, for example. These hypothetical particles, first proposed to solve a puzzle in particle physics, could also be the missing ingredient of dark matter. Unlike the bulky protons and neutrons we're made of, actions would be fantastically light, 1 trillion times less massive than an electron, flooding the cosmos like an invisible quantum fog. Their existence would arise from a subtle asymmetry in the strong nuclear force, a tweak to the equations that might explain why the universe favors matter over antimatter. If actions are real, they'd interact so weakly with ordinary matter that they could pass through Earth as if it weren't even there. Yet their combined gravity would sculpt galaxies into the vast, spinning structures we observe. Then there are WIMP, weakly interacting massive particles, another prime candidate. These heavier particles, predicted by supersymmetry theories, would be relics from the early universe, frozen out as the cosmos cooled. Imagine a cosmic game of musical chairs. In the searing heat of the Big Bang, particles and their superpartners constantly transformed into one another. But as the universe expanded and temperatures dropped, the music stopped. WIMP, left without partners, became stranded, drifting through space as dark matter. Detecting them would require ultra-sensitive experiments buried deep underground, shielded from cosmic noise, waiting for the rare moment a WIMP bumps into an atomic nucleus. The hunt for these quantum phantoms is already underway. Laboratories like the Action Dark Matter experiment use powerful magnetic fields to coax actions into revealing themselves, converting them into detectable photons. Meanwhile, detectors like Zeno NNT, submerged in Italian mountains, watch for the faintest flashes of light when a WIMP collides with liquid xenon. Even space-based telescopes join the search, scanning for gamma rays or other signals that might betray dark matter's presence. But here's the tantalizing possibility: dark matter might not be just one thing. It could be a mix of particles, each born from different quantum fields, each leaving its own fingerprint on the cosmos. Some might clump around galaxies, while others flow in vast, diffuse streams. Some could even interact with each other through forces we've yet to discover, weaving an invisible quantum web beneath the universe we see. If we do find these particles, the implications would stretch far beyond astrophysics. Confirming actions or WIMP would mean discovering entirely new facets of quantum theory, perhaps even uncovering connections between the forces we know and hidden dimensions. It would rewrite our understanding of how the universe evolved, how structures formed, and why matter survived annihilation in the early cosmos. The search for dark matter isn't just about solving a mystery. It's about peering into the quantum shadows where the next revolution in physics might be waiting. General relativity paints gravity as the bending of space-time, a cosmic trampoline where planets and stars create dips that guide their orbits. Yet zoom into the quantum realm down to the Planck length, a scale so small it makes atoms look like galaxies, and this elegant picture shatters. Here, space-time itself should churn with violent fluctuations, a frothing sea of quantum foam where the smooth curves of relativity dissolve into chaos. This is the frontier where Einstein's masterpiece meets its limits, and where the quest for quantum gravity begins a theory that could stitch these two realms together into a single, unified fabric. The challenge is staggering. Quantum mechanics thrives on probabilities and particles, while general relativity deals in deterministic geometry. One theory dances with uncertainty, the other charts the universe's grand architecture. To merge them, we might need to rethink space-time itself. Could it be an emergent property, like the surface of a lake arising from countless water molecules? Some theories suggest space-time isn't fundamental but woven from deeper quantum threads, just as temperature emerges from the jostling of atoms. Loop quantum gravity, for instance, proposes that space is built from tiny, indivisible loops, a pixelated cosmos where geometry itself is quantized. Black holes might not crush matter into singularities, but instead reach a smallest possible volume, rebounding in a cosmic bounce. String theory takes a different path, replacing particles with vibrating strings whose harmonies create all forces, including gravity. But to make the math work, strings demand extra dimensions curled up so tightly we've never noticed them, like ants oblivious to the third dimension as they crawl along a wire. These hidden dimensions could be the key to gravity's quantum behavior, with gravitons, the hypothetical carriers of gravitational force, leaking into them, explaining why gravity feels so weak compared to other forces. Yet for all its elegance, string theory remains notoriously hard to test. Its energy scales far beyond our current colliders. Then there's the holographic principle, a radical idea that our three-dimensional universe might be a projection of information stored on a two-dimensional surface, like a movie encoded on a DVD. If true, gravity wouldn't be a force in the usual sense, but a consequence of this cosmic encoding, an illusion born from deeper quantum interactions. It's a concept that blurs the line between reality and information, suggesting the universe might be more like a vast quantum computer than a collection of objects in space. The stakes couldn't be higher. A working theory of quantum gravity wouldn't just reconcile relativity and quantum mechanics, it could unlock the universe's earliest moments, revealing what happened at the Big Bang or inside black holes. It might explain dark energy or hint at hidden layers of reality. And while the math is daunting, the payoff could be a new lens through which to see existence itself. One where space-time, matter, and energy are threads in a grander tapestry we're only beginning to unravel. Until then, the search continues, a puzzle as profound as the cosmos it seeks to explain. What if everything you see around you, the depth of a canyon, the curve of a planet, the vastness of space, is nothing more than an illusion, a shadow cast by a hidden layer of reality? This is the startling claim of the holographic principle, a theory that suggests our three-dimensional universe might be a projection from a two-dimensional surface, like a cosmic hologram. The idea didn't come from science fiction, but from the study of black holes, where physicists discovered something peculiar. The maximum amount of information a black hole can contain isn't proportional to its volume, but to its surface area. It's as if all the data describing everything inside, every star, every atom, every photon, is somehow painted onto the event horizon, the black hole's outer boundary. This revelation led to an even wilder thought. If black holes encode their interiors on their surfaces, could the entire universe work the same way? Imagine a glass sphere with a movie projected onto its inner surface, creating the illusion of depth inside. The holographic principle proposes that our reality operates similarly, with all the information needed to describe every particle, force, and interaction in the cosmos stored on a distant, two-dimensional boundary we can't see. Your experience of reading these words, the sensation of depth and solidity around you, none of it would be fundamentally real, just an extraordinarily convincing projection. But how could this possibly work? The math points to quantum entanglement, the same spooky connection that links particles across space. Every bit of information in the universe might be woven together through these invisible threads, creating a network so dense that it forms a lower dimensional blueprint for our higher dimensional experience. Think of it like a QR code, a flat, pixelated image that contains all the data needed to reconstruct a complex, three-dimensional object when scanned. The universe could be a cosmic version of this, with the true source code of reality existing on a distant two-dimensional screen. The implications are staggering. If the holographic principle is correct, it could solve one of physics' biggest puzzles: how to reconcile quantum mechanics with gravity. In this framework, gravity wouldn't be a fundamental force but an emergent phenomenon, arising from the way information is encoded and processed on the boundary. It's a radical departure from Einstein's view of spacetime as a smooth, flexible fabric, but it might be the missing link that unites the quantum and cosmic scales. Skeptics argue that the principle remains untested, a beautiful idea without experimental proof. Yet tantalizing hints are emerging. Some models of the early universe suggest that quantum fluctuations in the primordial plasma, the seeds of all cosmic structure, could carry holographic signatures. Others point to anomalies in high-energy particle collisions that might reveal hidden dimensions or information bounds. Even if the theory isn't fully confirmed, it's already reshaping how we think about space, time, and the nature of reality itself. The holographic principle doesn't just challenge our intuition, it obliterates it. If true, the solid, tangible world we navigate daily is nothing more than a shadow play, a grand illusion spun from quantum data we can't yet perceive. It suggests that the universe is far more interconnected, far more mysterious than we ever imagined. And if that's the case, then the ultimate truth of existence might not lie in the stars or the atoms, but in the hidden, two-dimensional canvas from which all things emerge. Time feels like the most relentless force in the universe, always pushing forward, never pausing or rewinding. But here's the paradox. While our everyday experience screams that time flows in one direction, the fundamental laws of physics don't actually care which way it goes. Take a game of pool, for example. If you filmed the balls scattering after a break and played the footage backward, the motion would still obey Newton's laws. The equations work just as well in reverse, yet we never see shattered glass spontaneously reassemble or coffee unstir itself from milk. This is the enigma of time's arrow. Why does the universe have a preferred direction when the microscopic rules seem perfectly symmetrical? The second law of thermodynamics offers the classic explanation. Entropy, a measure of disorder, always increases over time. Think of a sandcastle on the beach left alone. It crumbles into chaos, never the other way around. But zoom into the quantum realm and this tidy story unravels. Quantum mechanics treats time as reversible at its core. A particle's wave function evolves smoothly backward or forward in the equations, with no inherent preference for past or future. So how does the irreversible march of time emerge from these time-symmetric rules? One compelling answer lies in quantum decoherence, the same process that collapses superpositions into definite states. When a quantum system interacts with its environment, whether it's a photon hitting a detector or a molecule jostling in the air, its delicate quantum states spread irreversibly into the surroundings like ink dispersing in water. This constant leaking of quantum information creates an effective arrow of time, even if the underlying laws don't favor one direction. It's as if the universe starts with a pristine, low-entropy state, like a perfectly stacked deck of cards, and every interaction shuffles it further toward disorder. The Big Bang might have been that initial orderly state, setting the cosmic clock ticking, but some physicists go further, suggesting time isn't fundamental at all. In loop quantum gravity, for instance, spacetime itself is woven from discrete quantum loops. Time could emerge from their interactions, much like temperature arises from the motion of atoms. Without these underlying quantum processes, time might not exist as an independent entity, just a useful illusion born from our limited perspective. Imagine watching a movie frame by frame. The illusion of motion only appears when you step back and see the sequence as a whole. Similarly, time might be a collective effect, not a built-in feature of reality. Then there's the tantalizing connection to quantum entanglement. Every time particles become entangled, their shared quantum state carries a kind of timestamp, a record of correlations that can only grow as the universe expands. This ever-expanding web of entanglement might be what we perceive as the flow of time, with the past solidified by countless quantum handshakes and the future open with possibilities. Some theories even propose that black holes, with their singularities where time seemingly ends, could be portals to understanding time's true nature. The stakes are cosmic. If time is emergent rather than fundamental, it could reshape our understanding of the Big Bang. Was there a before? Could time itself have quantum fluctuations, spawning baby universes with their own arrows of time? And what does this mean for the far future, when entropy reaches its maximum and the universe becomes a featureless sea of particles? The answers might lie in the quantum fabric of reality, where time isn't a river but a tapestry woven from threads we're only beginning to untangle. Quantum teleportation sounds like something ripped from a sci-fi blockbuster, but in labs around the world, scientists are already doing it, not by transporting matter through space, but by beaming the very essence of quantum information from one particle to another, instantly and without a physical connection. Here's how it works. Imagine you have two entangled particles, like a pair of quantum dice that always land on matching numbers no matter how far apart they are. If you manipulate one, say, change its quantum state, the other instantly reflects that change, as if they're sharing a secret faster than light could ever travel. This isn't magic, it's the eerie power of entanglement harnessed for teleportation. The process starts with a third particle, the one whose quantum state you want to teleport. By performing a special type of measurement on this particle and one of the entangled pair, scientists can effectively erase its original state while encoding that information onto the remaining entangled partner, no matter where it is in the universe. It's like burning a letter and watching the ashes reform into identical words inside a locked vault miles away. The original is gone, but its essence has been perfectly recreated elsewhere. This isn't just theoretical. Researchers have teleported quantum states across distances exceeding 1,000 kilometers, using satellites to link entangled photons between ground stations. The implications are revolutionary, especially for secure communication. Quantum teleportation could form the backbone of unhackable networks, where information is transmitted not through vulnerable cables or radio waves, but through the unbreakable bonds of entanglement. China's Misha satellite has already demonstrated this, teleporting quantum keys between continents to encrypt messages with perfect security, and this is just the beginning. Future quantum internet could rely on teleportation to connect ultra-secure nodes across the globe, enabling everything from fraud-proof voting systems to private communications shielded from even the most advanced cyber attacks. But the real cosmic potential lies beyond Earth. Imagine a probe sent to Alpha Centauri, 4.3 light-years away. Traditional radio signals would take years to reach us, but a quantum-entangled link could, in theory, allow instantaneous communication. Not faster than light signals, mind you, but a way to read changes in entangled particles here and there simultaneously, bypassing the speed of light bottleneck. It's not quite a subspace radio from Star Trek, but it's the closest thing physics allows. The challenge, keeping particles entangled over such vast distances, where cosmic radiation and interstellar dust could disrupt their fragile quantum states. Yet experiments with quantum repeaters, devices that extend entanglement like relay stations, are already underway. Of course, teleportation has its limits. You can't teleport a person or even a single atom. In this way, only information about a quantum state, and that information still needs to be sent classically to reconstruct the state on the other end, meaning it's not faster than light in practice. But what it lacks in Hollywood flair, it makes up for in sheer weirdness and potential. Quantum teleportation forces us to confront a universe where particles are so deeply linked that space itself seems like an illusion, where information can leap between points without crossing the distance between them. As we push the boundaries of this technology, we're not just building better networks, we're probing the very nature of reality. Every successful teleportation is a reminder that the quantum world operates by rules far stranger than our everyday intuition, rules that might one day let us reach across the stars without ever leaving home. Einstein never liked the idea of spooky action at a distance, the notion that particles could influence each other instantly across vast stretches of space. To him, it violated the bedrock principle of locality, the idea that objects can only be affected by their immediate surroundings. So in 1935, alongside physicists Boris Podolsky and Nathan Rosen, he crafted a brilliant thought experiment meant to expose quantum mechanics as incomplete. The EPR paradox, as it became known, imagined two entangled particles flying apart to opposite ends of the universe. Measure one's position, and you'd instantly know the other's faster than light could ever communicate between them. For Einstein, this wasn't just weird, it was impossible. There had to be hidden variables, unseen properties predetermined at the moment of entanglement, preserving a sensible, local universe. Yet decades later, experiments would turn Einstein's challenge on its head. When physicists like John Bell and Elaine Aspect put the EPR paradox to the test, they found something astonishing. Entangled particles really do coordinate their behavior instantaneously, with no hidden variables to explain the correlation. The universe, it seemed, was fundamentally non-local at the quantum level. Einstein's flaw wasn't in the math, it was in his intuition. He couldn't accept that reality might be probabilistic, that particles could remain mysteriously linked without any physical connection. But his resistance wasn't in vain. By pushing back so forcefully, he forced quantum theory to sharpen its arguments, refine its predictions, and ultimately emerge stronger. The EPR paradox didn't break quantum mechanics, it proved how unbreakable it truly was. This tension between skepticism and discovery runs deep in science. Every apparent flaw, every paradox is a doorway to deeper understanding. Take black hole information loss, another puzzle that seemed to violate quantum rules until holography and entanglement offered new ways to preserve information. Or dark energy, which once looked like a gaping hole in cosmology until it reshaped our view of the universe's expansion. Even today, quantum gravity remains a battleground of competing ideas, each one born from a crack in our current theories. What's striking about the EPR paradox is how it reveals the power of dissent in science. Einstein was wrong about entanglement, but his refusal to accept the status quo pushed physicists to ask harder questions, design sharper experiments, and confront the uncomfortable truths of quantum non-locality. Without his skepticism, we might never have uncovered the full strangeness of the quantum world, or harnessed it for technologies like quantum cryptography and teleportation. The greatest breakthroughs often come not from those who shout "Eureka," but from those who dare to say, "Wait, that can't be right." And as long as mysteries like dark matter or the measurement problem linger, that spirit of challenge will keep driving science forward, one paradox at a time. Quantum Darwinism flips the script on how we perceive reality. What if the classical world we take for granted isn't fundamental, but the result of a cosmic selection process? Picture a quantum system like an atom, existing in a haze of possible states spinning up and down simultaneously, a blur of probabilities. Now imagine this atom bombarded by its environment, photons, air molecules, even the faintest whisper of cosmic radiation. These interactions aren't just noise, they're a filtering mechanism, a quantum version of natural selection. Only the most resilient states survive this relentless scrutiny, while fragile superpositions crumble under the pressure. Over time, the system's quantum weirdness gets washed out, leaving behind the stable, objective properties we recognize, like an electron's position or a molecule's orientation. This isn't just philosophy, it's a mathematical framework explaining why we never see cats in superpositions or tables in two places at once. The key lies in redundancy, the way certain quantum states imprint themselves onto the environment. Consider a drop of ink in a turbulent river. The ink doesn't vanish, it spreads, leaving traces everywhere. Similarly, when a quantum system interacts with its surroundings, information about its state gets copied countless times into scattered photons, vibrating atoms, even the gravitational field. These copies aren't perfect, but they're durable, creating a consensus that observers like us can detect. It's as if the universe votes on which quantum states are real by amplifying them through environmental interaction. This consensus isn't arbitrary, it's shaped by the system's dynamics. Some states, like an electron's energy level in an atom, are robust, surviving decoherence to become classical. Others, like delicate superpositions, vanish into the quantum noise. This idea reshapes how we think about measurement. In traditional quantum mechanics, observation collapses the wave function, a mysterious, almost magical process. Quantum Darwinism offers a more grounded explanation. What we call measurement is just the environment's relentless copying of certain states until they become undeniable. The pointer on a lab instrument, the pixels on a screen, they don't record quantum possibilities but the outcomes that survive decoherence. Even our own brains, as they process sensory data, are part of this winnowing process, filtering quantum ambiguity into classical certainty. But here's the twist. This doesn't mean quantum effects disappear entirely. They're still there, humming beneath the surface, but they're drowned out by the roar of environmental interaction. In carefully controlled labs where scientists shield systems from decoherence, quantum weirdness thrives. A single ion suspended in a vacuum can exist in superposition for seconds, an eternity in quantum terms. Yet the moment it's exposed to the messy outside world, its quantum fragility reasserts itself and classicality takes over. The implications stretch far beyond interpretation. Quantum Darwinism suggests that objective reality isn't a given, it's emergent, sculpted by the interplay between quantum systems and their environments. It also hints at why the universe appears so consistent to different observers. When you and I look at a chair, we see the same solid object because our observations are tapping into the same environmental imprints, the same copies of quantum information that have been broadcast and reinforced. Critics argue that the theory doesn't fully explain why certain states are favored over others or how subjective experience fits into this picture. But as a bridge between the quantum and classical realms, it's a compelling step toward solving one of physics' deepest puzzles: how the fuzzy, probabilistic quantum world gives rise to the sharp, definite reality we inhabit. The answer, it seems, lies not in the particles themselves, but in the unrelenting sieve of the environment, a cosmic editor trimming the quantum multiverse down to the single, shared story we call the present. There's a quiet revolution happening in the way we think about the quantum and classical worlds, not as separate domains divided by some bright line, but as a spectrum where one bleeds into the other. Consider the humble buckeball, a soccer ball-shaped molecule made of 60 carbon atoms. In the 1990s, scientists sent these molecules flying through a double-slit apparatus, the same kind used to demonstrate the wave-particle duality of electrons. Astonishingly, the buckeballs produced an interference pattern just like single particles. Here was a molecule visible under an electron microscope, a speck large enough to almost touch, behaving like a quantum wave. If objects this big can dance to quantum rules, where exactly does the classical world begin? The answer lies in decoherence, the process by which quantum superpositions unravel as systems interact with their environment. A single electron can exist in multiple states at once because it's small enough to remain isolated, but a grain of sand, constantly bombarded by air molecules and light, loses its quantum coherence almost instantly. The transition isn't like flipping a switch, it's more like a fog lifting with quantum effects fading as complexity grows. Recent experiments push this boundary further. Researchers have observed quantum superposition in molecules weighing over 25,000 atomic mass units heavier than some proteins. These aren't just lab curiosities, they're proof that quantum behavior isn't confined to the microscopic. It's all around us, just usually drowned out by the noise of the macroscopic world. But what if some of that noise isn't just interference? Could quantum phenomena play a hidden role in larger systems? Take photosynthesis, where plants harness sunlight with near-perfect efficiency. Experiments suggest that the energy transfer in chlorophyll involves quantum coherence, with photons exploring multiple pathways simultaneously to find the optimal route. Even in our own biology, enzymes might rely on quantum tunneling to speed up chemical reactions, allowing particles to bypass energy barriers like ghosts passing through walls. These aren't exotic exceptions, they're hints that the quantum classical boundary is porous, with nature exploiting quantum effects wherever they provide an advantage. The implications stretch beyond biology. Some physicists speculate that quantum processes could influence macroscopic systems like the brain, where microtubules inside neurons might harness quantum vibrations. Others explore whether gravity itself, the force that shapes galaxies, could be the missing link that collapses quantum superpositions at larger scales. While these ideas remain controversial, they underscore a deeper truth. The boundary between quantum and classical isn't a fixed wall. It's a shifting frontier shaped by scale, environment, and perhaps even the fundamental laws we've yet to uncover. As experiments probe ever larger quantum systems, from superconducting circuits to levitated nanoparticles, we're forced to confront a universe far more interconnected than we imagined. The classical world we perceive may just be the tip of a quantum iceberg, its bulk hidden beneath the surface of our everyday experience. And if that's true, then the real question isn't where the quantum ends and the classical begins. It's how much of the quantum world we've yet to notice, humming silently beneath the familiar. Imagine unlocking the secrets of a new wonder material, one that could revolutionize energy storage or computing without ever stepping into a lab. Quantum simulations make this possible, acting as virtual laboratories where we can manipulate atoms and forces with the precision of a cosmic architect. Unlike classical computers, which struggle to model quantum systems by brute force, quantum computers speak the same language as the particles they simulate. They don't just calculate probabilities, they embody them, leveraging superposition and entanglement to explore quantum landscapes in ways that would take conventional machines millennia. Take drug discovery, for example. A single molecule's behavior depends on the quantum dances of its electrons, dances so complex that even supercomputers can only approximate them. But a quantum simulator could map every twist and turn, predicting how a potential medicine interacts with proteins or DNA at the atomic level. Researchers at companies like Roche and startups like Zapata Computing are already experimenting with this, simulating molecules like caffeine or lithium compounds to design better drugs and batteries. The goal: to shrink the decade-long, billion-dollar drug development pipeline into a fraction of the time and cost, all by testing compounds in a quantum sandbox before synthesizing them in the real world. Then there's superconductivity, the holy grail of energy efficiency. Materials that conduct electricity without resistance at room temperature could transform power grids, quantum computers, and even levitating trains. Yet despite decades of research, the mechanism behind high-temperature superconductors remains elusive. Quantum simulations could crack this puzzle by modeling electron interactions in exotic materials atom by atom, revealing how to engineer superconductors that work without extreme cooling. Google's quantum AI team has already taken steps in this direction, using a 53-qubit processor to simulate the behavior of electrons in a tiny patch of superconducting material, a glimpse of what's possible when we harness quantum systems to study quantum phenomena. But the most mind-bending applications lie in fundamental physics. Imagine simulating the birth of the universe itself, replaying the quark-gluon plasma of the Big Bang, or probing the quantum gravity that governs black holes. While today's quantum computers are too error-prone for such grand experiments, theorists are laying the groundwork. By encoding quantum field theories into qubits, we might one day test ideas about extra dimensions, dark matter, or even the holographic principle, all from inside a quantum circuit. The road ahead isn't without obstacles. Noise and decoherence plague current hardware, limiting simulations to small, simple systems. Yet breakthroughs in error correction and hybrid algorithms, combining classical and quantum processing, are steadily expanding the frontier. Companies like IBM and IonQ are racing to build machines with hundreds of logical qubits, while startups explore photonic and neutral atom architectures that could scale faster. What makes quantum simulations so transformative isn't just their speed, it's their ability to reveal the unexpected. Classical models rely on our assumptions, but quantum systems can surprise us, uncovering emergent phenomena or novel states of matter we'd never think to program. It's like having a conversation with nature itself, where the answers aren't just numbers but glimpses into the universe's deepest workings. Whether designing life-saving drugs or unraveling cosmic mysteries, quantum simulations offer a lens to see reality not as we approximate it, but as it truly is, one entangled atom at a time. Neutrinos are the universe's ultimate ghost particles, so elusive they can pass through light years of lead without a single interaction. Born in the hearts of stars, the fury of supernova, and even the quiet decay of atoms in your kitchen banana, these phantoms flood the cosmos, yet you'd never know it. Every second, trillions of them stream through your body, leaving no trace, as if you were made of fog and they were the wind. Their near-zero mass and indifference to electromagnetism make them nearly impossible to catch, yet their fingerprints are everywhere, from the sun's furnace to the explosive death of distant stars. What makes neutrinos truly bizarre is their ability to shapeshift, a quantum trick called oscillation. Imagine a chameleon that doesn't just change color but morphs into an entirely different creature mid-stride. Neutrinos do exactly that, flipping between three flavors: electron, muon, and tau. This metamorphosis isn't just a curiosity, it's proof that neutrinos have mass, a revelation that shattered the original Standard Model, which assumed they were weightless. The discovery earned the 2015 Nobel Prize, but it left a deeper mystery in its wake. If neutrinos oscillate, their masses must be immeasurably tiny, yet non-zero. Why and what other secrets might these oscillations hide? One tantalizing clue lies in the imbalance between matter and antimatter. According to physics, the Big Bang should have created equal amounts of both, leaving a universe that annihilated itself into pure energy. Yet here we are, in a cosmos made almost entirely of matter. Neutrinos might hold the answer. Experiments like Japan's T2K and the Deep Underground Neutrino Experiment DUNE are hunting for a phenomenon called CP violation, a slight preference for neutrinos over antineutrinos in their oscillations. If found, it could explain how matter eked out a victory in the early universe, tipping the scales toward galaxies, planets, and life itself. Catching these phantoms requires feats of engineering bordering on madness. Detectors like Super Kamiok, and in Japan a tank filled with 50,000 tons of ultra-pure water, lined with sensors so sensitive they can spot a single photon from a neutrino's rare interaction, operate deep underground, shielded from cosmic noise. Ice Cube buried in Antarctic ice uses a cubic kilometer of frozen water as its detector, waiting for the faint blue glow of a neutrino collision. These experiments aren't just about particle physics, they're cosmic observatories. When a star explodes, neutrinos arrive hours before light, offering astronomers a sneak peek at the universe's most violent events. The implications stretch beyond astrophysics. If neutrinos can oscillate, could other particles have hidden properties we've missed? Could their tiny masses hint at extra dimensions or undiscovered forces? Some theories suggest sterile neutrinos, a hypothetical fourth flavor that interacts only via gravity, might lurk in the data, a shadowy player in dark matter's puzzle. Others propose that neutrino research could unlock technologies like neutrino tomography, imaging Earth's interior or even detecting nuclear reactors from continents away. For now, these quantum phantoms remain half-seen, half-guessed, a reminder that the universe's most fundamental answers often hide in the most elusive places. Every neutrino detected is a whisper from the cosmos, a clue wrapped in a riddle. And as detectors grow more sophisticated, we're not just listening to their secrets, we're learning to speak their language, one ghostly interaction at a time. What if your thoughts, your memories, even your sense of self aren't just the firing of neurons but the shimmering dance of quantum particles? This radical idea, known as the quantum mind hypothesis, suggests that consciousness isn't merely an emergent property of classical brain activity. It's rooted in the strange, probabilistic rules of the quantum world. At the heart of this theory are microtubules, tiny protein structures inside neurons that form an intricate scaffolding. To most neuroscientists, they're just cellular infrastructure, but to physicists like Sir Roger Penrose and anesthesiologist Stuart Hameroff, they're potential quantum processors, humming with vibrations that could give rise to subjective experience. The theory hinges on a paradox. Classical physics struggles to explain how the brain achieves the unity of consciousness, the seamless integration of sights, sounds, and emotions into a single, coherent experience. Neurons fire too slowly, and their signals are too localized to account for the brain's ability to bind disparate inputs into a unified whole. But quantum processes, with their inherent interconnectedness, might offer a solution. In Penrose and Hameroff's model, called orchestrated objective reduction, quantum vibrations in microtubules persist long enough to perform computations, collapsing into definite states only when they reach a threshold of complexity. Each collapse corresponds to a moment of awareness, a flicker of consciousness emerging from the quantum foam. Critics, however, aren't convinced. The brain is warm, wet, and noisy, a hostile environment for delicate quantum states that typically require near absolute zero temperatures and perfect isolation to survive. Decoherence, the same process that destroys quantum superpositions in labs, should render microtubule quantum effects negligible in milliseconds. Yet proponents counter that biological systems might have evolved tricks to shield quantum coherence, perhaps through structured water molecules or resonant frequencies that extend quantum states. Some even point to anesthesia as indirect evidence. The way certain gases selectively shut down consciousness without disrupting other brain functions suggests a quantum mechanism, since these gases are known to interact with nonpolar regions of microtubules. The implications are staggering. If consciousness is quantum, it could explain why artificial intelligence, for all its computational power, lacks subjective experience. It might be missing the quantum layer. It could also bridge the gap between physics and philosophy, offering a scientific basis for the hard problem of consciousness, why and how physical processes give rise to inner experience. Some interpretations even venture into speculative territory, suggesting that quantum consciousness might connect to larger cosmic processes, embedding the mind within the fabric of reality itself. But the debate is far from settled. Mainstream neuroscience leans heavily toward classical explanations, viewing consciousness as an emergent property of neural networks without invoking quantum weirdness. Yet as experiments probe deeper, like studies searching for quantum vibrations in microtubules or investigating the role of entanglement in biological systems, the boundaries between the two camps may blur. Whether the quantum mind hypothesis ultimately holds or not, it forces us to confront the deepest mystery of all, the nature of awareness itself, and in that search, even wrong turns can illuminate paths we never knew existed. Quantum thermodynamics is like discovering that the universe's rulebook has a hidden chapter, one where energy doesn't behave the way it should. At the macroscopic scale, thermodynamics feels set in stone. Energy is conserved, entropy always increases, and perpetual motion is impossible. But shrink down to the quantum realm, and these laws start to bend. Here, particles can borrow energy from the vacuum itself, coherence defies classical decay, and microscopic engines run on the bizarre interplay of superposition and entanglement. It's as if the tiny world operates on a different set of physics, one where the impossible becomes probable. Take the concept of a quantum heat engine. In the classical world, a car engine converts heat into motion with well-understood efficiency limits, but a quantum version might exploit superposition to perform work in ways that defy Carnot's centuries-old efficiency boundaries. Imagine an engine where the working fluid isn't steam or gas but a single atom, existing in multiple states at once. By carefully tuning quantum coherence, the ability of particles to maintain phase relationships, such an engine could, in theory, extract more energy than its classical counterpart. Experiments with trapped ions and superconducting qubits have already demonstrated prototypes, revealing efficiency boosts when quantum effects like entanglement are harnessed. The catch: these systems are fragile, their advantages fleeting as decoherence kicks in. Yet the promise is tantalizing: machines that leverage quantum weirdness to push past the limits we once thought absolute. Then there's the mind-bending idea of information as energy. In classical thermodynamics, erasing information, like resetting a computer bit, always costs energy, a principle called Landauer's limit. But quantum systems blur this line. A qubit in superposition doesn't just hold a 1 or a 0, it holds both until measured. Carefully manipulating this state could, under certain conditions, reduce the energy cost of erasure or even recover energy from information itself. Researchers have toyed with this in labs, using nanoscale devices to probe the quantum information energy nexus. Some proposals suggest that future quantum computers might recycle their computational waste heat, turning errors into fuel. It's a paradigm shift. Information isn't just abstract, it's a physical resource as tangible as coal or sunlight. Perhaps the most startling quantum thermodynamic effect is vacuum fluctuations. Empty space isn't truly empty, it's a seething foam of virtual particles popping in and out of existence. Normally, these fluctuations cancel out, leaving no net energy. But place two ultra-close metal plates in a vacuum and something remarkable happens. The plates suppress certain fluctuations between them, creating a pressure that pushes them together. This is the Casimir effect, and it hints that the vacuum itself holds usable energy. Hypothetical quantum devices could, in theory, tap these fluctuations, extracting work from what appears to be nothingness. The challenges are monumental. Controlling such effects requires precision bordering on the absurd, but the implications rewrite what we consider free energy. What makes quantum thermodynamics so revolutionary isn't just the potential for better engines or batteries. It's the way it forces us to rethink the nature of energy itself. From the fleeting coherence of entangled particles to the ghostly whispers of the quantum vacuum, this field reveals a universe far richer, far stranger than the classical thermodynamics of steam engines and refrigerators suggested. And as we learn to harness these effects, we might just find that the smallest scales hold the keys to humanity's biggest energy challenges. The Standard Model of particle physics is one of humanity's crowning intellectual achievements, a framework so precise it can predict the behavior of subatomic particles to a dozen decimal places. Yet for all its brilliance, it's like a masterpiece with glaring holes cut straight from the canvas. It can't explain why the universe is filled with invisible dark matter, why gravity refuses to play nice with quantum rules, or why ghostly neutrinos, those cosmic shape-shifters, have any mass at all. These aren't small gaps, they're chasms, hinting that the universe operates by rules we've only begun to glimpse. Enter supersymmetry, or SUSY for short, a bold idea that every known particle has a hidden, heavier twin waiting to be discovered. If true, it would elegantly solve mysteries like dark matter, with the lightest supersymmetric particle being a prime candidate for the universe's missing mass. It could also unify the fundamental forces, suggesting that at unimaginably high energies like those just after the Big Bang electromagnetism, the strong and weak nuclear forces, and even gravity were once facets of a single sublime symmetry. For decades, physicists hoped the Large Hadron Collider would reveal these superpartners, but so far, the detectors remain silent. Does this mean Sussy is dead, or are we simply looking in the wrong energy range? The hunt isn't over. Next-generation colliders, like the proposed Future Circular Collider with its 16-mile circumference, could probe deeper, searching for whispers of supersymmetry in realms beyond our current reach. Then there's the enigma of extra dimensions. String theory suggests our universe might have 10 or 11 dimensions, with all but the familiar 4-3 of space and 1 of time curled up so tightly we've never noticed them. But what if some of these dimensions aren't microscopic? Brainworld cosmologies propose that our entire universe could be a 3-dimensional brain, floating in a higher dimensional space with gravity leaking into the bulk. This could explain why gravity is so weak compared to other forces. It's not confined to our brain like light and matter are. Experiments searching for deviations in gravity at tiny scales or anomalies in particle collisions could reveal these hidden dimensions, rewriting our cosmic address in the process. Meanwhile, neutrino physics is undergoing its own quiet revolution. We now know these phantoms have mass, but the standard model offers no explanation why. Are they harboring secrets about undiscovered particles like the hypothetical sterile neutrino? Or could their tiny masses hint at a connection to the Higgs field or even dark energy? Projects like the Deep Underground Neutrino Experiment are blasting beams of neutrinos through hundreds of miles of Earth to study their oscillations with unprecedented precision, hoping to catch clues about the universe's matter-antimatter imbalance along the way. The most tantalizing possibility is that these puzzles are interconnected, that dark matter, neutrino mass, and gravity's quantum fuzziness are all pieces of a grander theory waiting to be uncovered. Perhaps the next breakthrough won't come from a collider but from a telescope spotting the annihilation of dark matter particles, or a lab measuring gravity's behavior at quantum scales. Whatever the path, one thing's certain: the standard model isn't the end of the story. It's the prologue to a deeper, stranger understanding of reality, where every unanswered question is an invitation to explore further. The next revolution in physics isn't just coming, it's already unfolding, one experiment at a time. Manipulating the quantum realm isn't just a scientific challenge, it's a moral frontier. With every breakthrough, we're not just tweaking equations, we're rewiring the fabric of reality itself, and that power comes with profound ethical dilemmas. Take quantum biology, for instance. If we can optimize photosynthesis by enhancing quantum coherence in plants, should we? On one hand, it could revolutionize agriculture, feeding billions with crops that harness sunlight with near-perfect efficiency. But what happens when we start redesigning life at the quantum level? Would these super plants outcompete natural species, destabilizing ecosystems? Or worse, could quantum-enhanced organisms accidentally evolve traits we can't predict, turning well-intentioned science into ecological chaos? The line between healing nature and playing God blurs when we tinker with life's quantum machinery. Then there's the double-edged sword of quantum encryption. Promoted as unhackable, it relies on the fragility of quantum states. Any eavesdropping attempt disrupts the system, alerting users instantly. But what if governments or corporations weaponize this technology, creating communication channels so secure they enable unchecked surveillance or criminal activity? Quantum networks could democratize privacy, but they might also deepen the divide between those with quantum access and those without. Imagine a world where financial transactions, medical records, or even voting systems are locked behind quantum firewalls, rendering classical cybersecurity obsolete. The very technology designed to protect could become a tool of exclusion or control. Artificial quantum intelligence amplifies these stakes exponentially. Classical AI already pushes ethical boundaries, but quantum machine learning could explode those challenges. A quantum AI might solve problems in seconds that would take classical algorithms millennia, but at what cost? Could it crack encryption protocols that safeguard global infrastructure, or simulate human consciousness so accurately that it raises questions about rights for synthetic minds? The speed of quantum processing might outpace our ability to implement safeguards, leading to decisions made faster than human oversight can intervene. Picture an autonomous quantum algorithm controlling a power grid or military drone swarm, its thought processes occurring in a realm we can't fully observe or understand. These aren't distant hypotheticals. Quantum technologies are advancing faster than our frameworks to govern them. Unlike nuclear power or genetic engineering, which had decades of debate before widespread use, quantum applications are emerging in real time, with ethical guidelines struggling to keep pace. The conversation must extend beyond physicists and engineers. Philosophers, policymakers, and the public need a seat at the table, because the question isn't just can we manipulate quantum reality, it's should we, and who gets to decide. The answers will define not just the future of science, but the future of humanity's relationship with the universe's most fundamental layer. One thing's certain, the quantum age isn't just about discovery. It's about responsibility. Our journey into the quantum realm has been anything but ordinary. It's been a descent into a world where logic twists, particles communicate across galaxies, and the very act of looking changes what's there. We've seen how a single electron can exist in multiple places at once, how entangled particles defy the speed of light, and how the vacuum of space itself crackles with invisible energy. These aren't just abstract curiosities, they're the building blocks of everything: the stars above us, the devices in our hands, even the beating of our hearts. Yet for all we've uncovered, the quantum revolution is only beginning. Picture a future where quantum computers crack problems in seconds that would stump today's supercomputers for millennia, simulating new materials to solve climate change, designing life-saving drugs atom by atom, or unraveling the mysteries of dark matter. Imagine unhackable quantum networks securing global communications, or sensors so precise they detect gravitational waves from the birth of the universe. These possibilities aren't science fiction, they're the horizon we're racing toward, fueled by discoveries made in labs barely bigger than a grain of sand. But the quantum world isn't just reshaping technology, it's rewriting philosophy. If particles don't exist in definite states until observed, what does that say about the nature of reality? If entanglement binds the universe in unseen connections, could space and time be illusions? These questions blur the line between physics and metaphysics, inviting us to rethink everything from consciousness to the cosmos itself. The quantum realm doesn't just challenge our tools, it challenges our minds, pushing us to imagine a universe far stranger than our ancestors ever dreamed. What's most exhilarating is how much remains unknown. Every answered question unveils deeper mysteries. Is space-time woven from quantum threads? Do parallel universes branch with every decision? Could life itself harness quantum effects we've yet to discover? The pursuit of these answers isn't just academic, it's a testament to human curiosity, our relentless drive to peel back the layers of reality, no matter how counterintuitive they seem. So as we step back from the microcosm, remember this: the quantum world isn't a niche corner of science. It's the foundation of existence, hiding in plain sight, waiting to transform our future. The next breakthrough might come from a lab, a telescope, or even an unexpected flash of insight. Wherever it arises, one thing's certain: the universe's smallest scales hold its grandest secrets, and the adventure to uncover them has only just begun. Keep wondering, keep exploring, and stay open to the possibility that reality, when examined closely, is far more mysterious and more magnificent